Ok, donc si vous avez des questions en français, après, vous pouvez le demander en français, mais je vais parler en anglais parce que je suis plus confortable en anglais, mais si vous avez des questions en français, c'est aucun problème. Hi. So there's a problem in how cryptography is approached generally, which is that you have people who are focused on the practical side, and they develop practical applications. And if you're lucky, you end up having those people use standards, and they develop, something using, they read up on the academic side, and then they implement in a way that's good. And then you end up with practical cryptographic applications that are good and that work. For example, PGP is considered good. And then you have the other side, which is the academic side, and which develops a lot of theory, and that's good, because the theory is tested academically and it's battle tested and it's fine. But the problem in how cryptography is approached is that these two sides never really carry the load of each other. So you either have really good crypto that's being developed in academia and locked in academia, or you have really good crypto that's being developed practically and then never explored from an academic or from a theoretical context. And as a result, you have a lot of really good crypto that never gets implemented, and you have a lot of crypto that gets implemented, and that's not very good, because the whole spectrum of the research is not considered. People who are doing practical stuff don't consider the theoretical side. People who do the theoretical side don't consider the practical side. So in this talk, I wanted to do both. I was hoping to do both. And what this talk is about is focusing on a new effort that I'm trying to do regarding usable cryptography. What I mean by usable cryptography is that the developing of standards, of tools, of practical apps, tools that you can use, but as well as theoretical standards, so that in the future, or when you want to encrypt something, or when you want to use an app that's preserving your privacy, the barrier to entry is smaller, and the access to this application is more immediate. But in order to start, and since I'm starting with a primer on the history of web and browser cryptography, you need to go back to the Stone Age, long time ago, known as 2012, where dinosaurs roamed the earth. It really feels that way sometimes. So if you are familiar with anything I have ever done before, you might know that I am a huge proponent of transforming the browser into a platform where you can in fact run client-side cryptography, because I think that's the future. And so in 2012, when people still lived in caves, if you would believe my presentation, browsers were considered an environment that is hostile to cryptography. And so even though, the browser, it was the case that we were doing all our instant messaging in the browser. We were doing all our email in the browser. Google Docs, Drive, Dropbox, OneDrive, all of that stuff in the browser. And that was great. It was making our lives easier. And at the same time, the browser was hostile towards measures that would make it so that you had client-side encryption for all your data. So implementing something like PGP in the browser was impossible. And there were many good reasons why this was the case. So first you had the malleability of the JavaScript runtime, which means that the language that we're using to program client-side stuff on the browser is called JavaScript. And JavaScript, the runtime, when you're running code, the space in which this code is running can be changed at any time. It's not like C, where you compile something and then you run it and then you get a buffer overflow and then you change the runtime anyway, kind of, because you're changing the RAM. But it was different than that in the sense that code could be injected if you had any vector for injecting the code like XSS. It's a bad idea to run encryption in that context. Also, encryption generally, when you want to implement encryption tools, you need access to the low-level aspect of the system, which means that if I'm storing an encryption key in the system memory, later I need low-level access to erase that key from the system memory, right? Because I want to make sure it's gone from RAM, and other things like that. There's also random number generation, which requires this kind of low-level system access if you're planning to do it securely. And this is not available in JavaScript because of the memory management, garbage collection, so on. So that was one big problem. Another big problem is that code delivery is a chicken and problem in the browser. We're used to using desktop applications where you download an application once, and then you run it, and then you're done. And then to verify the code of an application, maybe you compiled it from source code, it's available on your desktop, and you know where it came from. And if it's signed, if it has like a SHA-1 hash or a signature or something, it's authentic. But when you're loading code in a browser for your web application, say you're opening Gmail, you are loading the programming for Gmail every time from scratch. And this means that if you loaded a good Gmail code one time, there's no guarantee that the next time you use Gmail, the code is going to be good. Because the next time you use Gmail, maybe someone targets your IP address and serves you a JavaScript file that compromises the safety of that particular Gmail session while not serving the file to others. They can just serve it to you. Because the delivery of the code could be targeted, it's ephemeral, and it happens a lot. So there wasn't a way to verify that when I'm using an app in a web browser, I'm actually using the app that I think I'm using. And even if I am using the app that I think I'm using this time, that doesn't mean that it's going to be the same one that I'm using next time. And so, you might be thinking, why not use SSL? Why not use HTTPS? Maybe that solves the problem, right? And so this actually is the most annoying thing to me in 2012 was this question, and it might be a surprise. There was a very big article that says, yeah, you can use SSL. It's harder than it sounds, but you can safely transmit JavaScript crypto to a browser using SSL. The problem is, having established a secure channel with SSL, you no longer need JavaScript cryptography, you have real cryptography. And so actually, this one quote, is the embodiment of why the general community did not understand the special thing that was given by being able to do client-side JavaScript in the browser. Because they were comparing it to SSL, and they said that SSL, if you do SSL, then you're doing real cryptography. And you don't need JavaScript cryptography because SSL replaces the benefits of JavaScript cryptography. So you don't need to bother with JavaScript cryptography anymore. And also, they actually said that, as if deploying SSL was harder than making a JavaScript crypto system, as if getting a certificate off Gandhi.net, or like breaking into a certificate authority and taking your own certificate was actually harder than rolling your own JavaScript crypto system, which is ridiculous. But the thing is, JavaScript crypto is not meant to compete or replace or be like an easier shim out of SSL. The thing with JS crypto is that when you encrypt something on the client side, then you send it to the server itself cannot read it. With SSL, you just have transport layer security. So when the data actually gets to the server can still read it. And TLS is wonderful for that. It's doing its job most of the time. But that's not what we're trying to replace. We're trying to make it so that you use JavaScript crypto with SSL, so that SSL secures the data until it gets to the server. And once the data gets to the server itself cannot read it. And then the server itself, the provider itself, Google, Facebook, do not have access to your data. And that's what JS, like client-side cryptography in the browser, was meant to offer, which is very different and amazingly offers things that SSL cannot ever offer. So I am right to say, I think, that in 2012, no one saw the value of JavaScript cryptography. JavaScript was shifting from the language of the web to the language of everything. Even today, if you talk to people who work in larger, more established companies, they still think that JavaScript is this language that you use, you basically Adobe Flash to make animations and cool stuff. But this is really not the case. JavaScript is a functional programming language that is being used to develop desktop applications, server applications, web applications, mobile applications. And it's quickly becoming like a unified language where you have compilers because of enterprise competition, because Google and Microsoft and Apple are killing each other to make faster and faster JS compilers and better JS compilers. It's almost as fast as Java, and it's 4 or 5 times faster than Python and Ruby, and faster than Perl even. And so you have this incredibly fast language, incredibly well-supported language that's being used to develop applications on more platforms than any competing language, except maybe for C because it's a systems language. And then at the same time, making sure this language can do encryption properly. Why would you? Just use SSL. This was the general understanding, which to me was very frustrating. And so moving on to when people discovered agriculture, which is 2013, I was working on this project, which you've probably heard of in a not so nice way, called CryptoCat, which is basically, it was an attempt to do encrypted chat with the browser. So basically OTR, the standard for encrypted chat, but in the browser, because then you wouldn't have to install anything. You would just like download and install a browser extension, and then you had OTR immediately. And so the goal was that let's try to see how far we can leverage JS crypto and browser technologies to offer a secure drop-in replacement for OTR. Or pigeon OTR, because it is OTR, CryptoCat is OTR. And at the same time, limiting the barrier to entry as much as possible. Trying to get over the fact that when people want to use crypto, generally, they seem to have a really hard time. So it was supposed to be accessible no matter your background. Okay, so great. This was what I tried to do. What are the basic needs of this application? Not very difficult to guess. So you need secure primitives, so you need secure cryptographic functions. You need to implement AES correctly, SHA-2 like hashing correctly, elliptic curve Diffie-Hellman, the public key exchange function, you need to implement it correctly. Sure. Also, you need to be able to securely generate pseudo-random numbers. Because in order to generate private keys in a public key crypto system, you need random numbers that are really random, that are very hard to guess. And doing that generally, so how do people generally make random numbers on computers? Computers are deterministic machines, right? The way people make random numbers on computers is by accessing the low-level API of computers. So they measure, for example, like they take the hard drive spinning speed, the CPU temperature, the fan speed, the current time, which by itself is a terrible seed, and other things, and then they merge them all together, and then they get like a very high source of entropy, like unguessable factors, and then they use that to derive random numbers, pseudo-random numbers. And so you can't do that in JavaScript, clearly. JavaScript doesn't have access to the fan or to the, doesn't have access, just it's very high level. So that was one thing you needed to solve. And also the problem of secure code delivery, right? Because, you know, I said websites were throwing you the code from scratch every time with no guarantees. So cryptographic primitives. Let's start with the first one. So JavaScript is a language that, like many scripting languages, like Python, like Ruby, and others, relies on numbers that are 64-bit floating point. So in public key cryptography, Diffie-Hellman RSA said you have numbers that are much larger than 64-bit floating point. You have prime numbers that are thousands of bits large. And so we took a library and maintained it and improved it so that now you can have big integers functional in JavaScript, and JavaScript can do big integers. It can handle a 1,000-bit prime number, no problem, 4,000 bit, who cares? And also some algorithms were computationally expensive to do in JavaScript. Also in any language, really, unless you do it in C or assembly, which is basically things like RSA or especially DSA. And how would you do that in the browser without locking up the user's browser? So basically, in 2013, there was this then new technology called web workers, which means that you can basically multi-thread and create like a JavaScript separate thread, literally like another CPU thread, and then it would do stuff for you, and then do message passing. And so you had concurrency in JavaScript in 2013, which is incredible at the time as what is happening. And so we use that to be able to generate, do computationally expensive operations, which are sometimes necessary in cryptography without really locking everything up. Then, cryptographic primitives. So, you know, you needed to have people who knew what the heck they were doing implementing AES in JavaScript. And so here's the thing, which is that for a lot of people, especially if they're more seasoned people, like who grew up programming in like C and Java, when you tell them primitives in JavaScript, they're like primitives in Visual Basic or primitives in Adobe Flash or primitives in QBasic. It sounds really strange to them. Like, why would you do that? And the thing is, this is actually a big misunderstanding. So, challenge round. Who can tell me which one of these implementations of one round of AES is from JavaScript and which one is from OpenSSL? Both of them are standardized. One of them is from the Stanford University JavaScript crypto library, and the others is from OpenSSL, which all of you know about. Trick question. It's impossible to tell because the syntax is exactly the same. So as you can see, as I said before, JavaScript is a functional programming language, and it takes a lot from C in terms of syntax, and also, I mean, you could make the code look like Haskell. It worked like Haskell if you really wanted to, and actually, it doesn't take that much effort. Also, JavaScript is really easy to do bugs in a lot. So this was actually a super huge bug in CryptoCat last year, June 2013. Basically, JavaScript has something called dynamic typing. The slide says weak typing, but that's wrong. Which is that you can define a variable as a string, and then later it becomes a number, and then it becomes a decimal or a boolean or an integer. No one knows. Like, just you can flip the type as you like, and there's no really type separation a lot in JavaScript. You can query the type of a. There are types, but they're very easy to switch between. And so as a result, if you think that you're generating 32 random bytes, guess again, you were generating 32 random decimals. And so that private key that you thought was 32 bytes is actually 32 decimals, which means that it has a security of about 2 to the power 30. And that has been in your code base for 8 months. So JavaScript, use it for crypto. Clearly, there are problems with developing secure stuff with this language as well. So aside from that, you have also secure pseudo-randomness, which I discussed before. Right? So JavaScript comes with an amazing function called math.random, which relies on guessable, unfortunately, entropy sources. Unless you're using Opera, for some strange reason, Opera math.random is like cryptographically secure. I don't know. I actually sent an email to the Opera guy, like, is it true? And he's like, yes, we made sure that all random functions in Opera are cryptographic. Okay, fine, thanks, man. And so, but you shouldn't do that anyway. Now there's a new standard called window.crypto.getRandomValues, and it's actually part of a much bigger thing called window.crypto, which I'll get into later. And it uses ViewRandom if you're lucky, and then you're fine. So that problem solved. And then you have code delivery. So thank you, Google Chrome, for solving the problem, for leading the way on code delivery. They did that by basically introducing something called Chrome apps, because they launched the Chromebook, right, with Chrome OS. And then basically they wanted the Chromebooks to have app-like things. So you install, instead of running web apps on it, you could install like web apps that behave like desktop apps on your Chromebook. And then they also said, okay, we did that for Chrome OS and for Chromebooks, why not also make it for Chrome? So as a result, all of Chrome now has a thing called, except mobile versions. I hope they do it for mobile versions. Has a thing called Chrome apps, which is basically you download a web app and it installs inside Chrome and it becomes a desktop app. And then it has sandboxing, code signing, runtime, JavaScript runtime modification prevention. It has like amazing features, like the JavaScript runtime being modified. Nope. Sandboxing, even code signing with certificates and automatic updates. It's like an app store, and it does that for web apps. And you can install them locally, and they run offline. So the Chrome app the Chrome app model is this like the most underappreciated thing that Chrome has ever brought to the web. It's actually really amazing. In terms of what it offers in security and usability of web applications. It makes them installable as desktop applications, and the user interface is amazing. It even has like a desktop shortcut and everything. So that's really cool and really well done. I'm a huge fan of what they did there. And it solves, the code delivery problem for web applications. There's also, I should mention, a project called Node Webkit, which lets you develop desktop apps with desktop GUIs on multiple platforms, like on Windows and Mac and Linux, with Node, which is amazing, even more amazing, because Node has low-level APIs, like file sockets and raw sockets even, disk APIs and things like that, which are generally lacking, of course, from JavaScript. So that's cool. And also the Chrome app model has low-level APIs. For example, it lets you do Bluetooth connections and stuff like that. Um, and so in some cases, actually, signed browser apps have a advantage over regular desktop apps in the sense that Chrome guarantees them this Chrome-specific sandboxing, which many desktop apps do not have. And so that's actually really cool. So which brings us to today. You know, this was the background towards like all of these technologies that I'm explaining right now. These are technologies that I wanted to see improved because ultimately they bring privacy technologies and encryption technologies to the web, which is where they're going to reach people more, which is where we're going to get over the problem of what PGP has been causing generally in terms of being unusable. So now, 2014, today, there are chariots and vegetables. Okay, great. So there's the W3C started working, basically it's the organization that does web standards. They're the people who maintain what HTML means, like the definition of the HTML standard, the CSS standard, and so on. They wanted to do native cryptographic primitives in the browser. So instead of importing an AES library, your browser now does AES in JavaScript immediately by itself. JavaScript has AES built in. And that's really amazing, and it was called the Web Crypto API project. And it was a solid chance to mitigate things like side channel attacks, where there's a problem with your AES implementation and someone can measure the timing and someone can measure the power analysis and break your AES or your elliptic curve Diffie-Hellman implementation. So this is really cool. It's missing a couple of features right now. It needs modern key exchange algorithms like Curve 25519, and also it needs a way to securely store keys. Because right now, we're not going to store your encryption keys and cookies in the browser because that's so dumb. You know, there needs to be a way to do that other than like local storage or IndexedDB, because that's slightly less dumb, but only slightly. So also, there was a sudden acceptance. You know, people were trying to suddenly, people were trying to see the good side of JavaScript cryptography. Very welcome change, really. I mean, Thai Duong was a huge opponent for the longest time, and then he's on Google working on a GPG extension for Gmail in JS Crypto, which is what Google launched recently. And then Microsoft publishes the JavaScript cryptography library of Microsoft, which is quite a shock, really. You know, everyone, you know, if you have issues with JavaScript crypto, wait until you see C crypto. It blew my mind because actually JS Crypto was really unpopular for 2 years, and it's still like kind of unpopular today. But this has changed a lot. And so to close up with like the history lesson, I would like to see a change to dynamic typing in JavaScript. And it doesn't have to affect dynamic typing. Like JavaScript is not going to switch to a strongly typed language because no language changes radically like that, of course. But one really legit thing that we can do is that basically you can have your var k equal 5, and then if you do k plus meow, you get 5 meow because it changes into a string. But also you can do var number k, and then it locks it into as a number. And so that would be really amazing if we could do that, especially now because they're kind of like being adventurous in JavaScript. They're doing like array buffers and typed arrays, and then those have direct access to memory. So if I store a value in an array buffer and then I clear the array buffer, the memory is cleared immediately, and because it's directly into RAM, it kind of like goes around the garbage collector a little bit. So they're doing that. Why don't they do that too? Okay, hopefully more exciting part of my talk. What I'm working on today is a new protocol for usable encryption, and it's not just a protocol. I want this protocol to be accessible. I wanted to innovate on how file encryption and sharing works. And I want to build a tool for it, but I also want it to be part of other tools that you build to make it more universally accessible and to make it so that it actually helps normal people. So it's called miniLock. It has a cute smiling lock as the logo, and it's file encryption software that does more with less, because it does in fact do more with less complication and less code and less things. Okay, so the current status for file encryption. I think I'm right to say that PGP, GPG, is the super #1 leader right now in the field. If you want to send something encrypted, you send it via PGP. And there's a use case, PGP is used a lot for files. And it has classic public key management. There's also the Carmen Sandiego of cryptography, which is this. I don't know what happened. So that's my slide on that. And key management is really bad. Okay, so let's see how key management, going back to PGP, let's see how key management works. What do you do when you get a new PGP account? You generate your keys, and then you store them on your disk with a passphrase, like your private key has a passphrase stored on disk. And then your public key, it's super long, so you send it via email, or you put it on your website, or you put it on a key server. And then when you get the public key of someone else, or when they get your public key, you verify via fingerprints, and then you have to do key management, and so on. And so this is like, I mean, if I was about 2 years younger than I am today, this would have been the title of my slide. This is not going to be the title of my slide. This is going to be the title of my slide. This is not convenient, and we can do a lot better. So let's acknowledge here that PGP is awesome and amazing at everything except understanding the world we live in. It's in the platonic world of forms where PGP exists as a perfect floating cube of mathematical beauty. PGP is neat. However, in the world of today, where, people, PGP is not so good. So let's break it down into 4 things, okay? So here, numbers. 1, 2, 3, 4. The first thing is generating keys. The second thing is saving them on disk with a passphrase. And the third is sharing long public keys via email. And the fourth is storing other people's keys, authenticating their fingerprints, and managing those keys. I claim to be able to improve on all those things radically. So, no key storage, no key files. What is happening? miniLock asks you for a passphrase and uses that passphrase to generate your key identity. So, which means that if you enter your miniLock passphrase on one computer, on this computer, and then you get your identity on this computer, you get your public key, you can encrypt, send, and receive files on this computer based entirely on your passphrase. And then if you go on another computer, and so this is like this computer was not connected to the internet, there's no internet traffic going on. So if you go to another computer and you enter the same passphrase, you get again the same key identity. And so if alarm bells are going in your head, if you're any crypto people in the room, I'll explain how this works, and it's not that broken. It does sound a bit weird at first, so I completely understand. Enter, so basically, and nothing is ever stored. There's no key storage, there's no key file, etc. And also the public keys. So private key and key files. In that previous slide, private keys and key file storage and management of key files. Big improvement. Now, what about public keys instead of private keys? So public keys are so small. Look at how small they are. This is my public key. It fits on my business card. It fits on my Twitter. In fact, not only can I fit it in my Twitter bio, but I can fit it in a tweet twice. I can put it 2 times. I don't know why I would do that, but I did do that because it was cool. This is really nice because actually it's so small that it's like the same size almost as the fingerprint of a PGP key. So even the fingerprint of your PGP public key is longer than this, or maybe the same size or a bit shorter. I don't know. It's around this length. So public key is big improvement. Then you have the user flow. You can enter your passphrase. I already explained this. You can enter your passphrase on a miniLock capable computer, and then you get the miniLock ID, your miniLock ID, which is always the same. That little public key I showed you earlier. On any computer where you enter your passphrase, you will get that same ID, and then you can share it. You put it on your website, put it anywhere, put it on your email signature, and then you can receive files sent to that ID and send files from that ID. So this is substantially better because there is no private key storage or management. There is no managing long key identities of others. They're so small. And they're so small, in fact, that, as I said before, they act as a fingerprint. So this is a brief overview of the technical, theoretical aspect. What about the software itself? The software itself is easy to use. You can also use it for your own use. And it runs on any computer, because it's a Chrome app, which runs on Chrome OS, Windows, Linux, and Mac. And also, independent developers have ported it to Windows, Android, and also Python and other platforms. So now there's independent libraries that I have not checked myself, so I don't know whether they're safe, but they're there. So nice features. You can send to multiple recipients, and it doesn't. There is no overhead. There is like virtually no overhead on the file size or the performance. The miniLock IDs of recipients and senders are anonymized. So basically, when I send a miniLock file, say I am sending a miniLock file to the person at the end of this room, and then it is intercepted by someone in the middle of the room. The person in the middle of the room who intercepts it, actually, even if they analyze the file, they cannot tell who the sender is of a file or who the recipients are. And then if I'm sending it to multiple recipients, if a valid recipient decrypts the file, even the valid recipient cannot tell who the other recipients are. So there's complete anonymity. But however, a valid recipient can confirm that I am the sender. So if you are able to receive the file, you are a recipient, you can tell also that I was the correct sender. But aside from that, anyone who intercepts the file cannot know to who it was sent or who sent it. They can know to how many people it was sent, but that's about it. Also, it's fast. It's about 10 megabytes a second, so not really that fast, but it's okay. It retains file names on decryption, so even if you change the file name of the miniLock file, when you decrypt the file, it restores the original file name, which is a nice feature that seems to be lacking. And also, you can make it encrypt entire folders automatically. The best thing of all is that the specification, the design specification and the crypto specification is peer-reviewed, and the code is fully audited. So there has been some peer review, a lot of peer review, I would say. There's also a unit test kit that comes with the software, which is that you simulate entire user flow with randomized use cases, and it makes sure that everything works according to tests. It's good, means the software is stable and reliable. And also the code base and the design is simple to understand and highly portable. You can install it, the code base comes with design documents, specifications, etc. And you can install it in your own application. Your own app can be miniLock ready. And so, how does it work? Reliance, so the public key, the key exchange stuff, the public key cryptography stuff is actually elliptic curve crypto. And I'll be talking about that. And there's also secure passphrases are basically guaranteed via a measure that I'll also talk about, and also the script key derivation function. And also it has an innovative header construction that does the cool things like anonymize the sender and the recipients and other nice things. So the cryptographic primitives are actually all part of NACL. NACL or SALT or whatever it's known as is a cryptographic library developed originally by Dan Bernstein of the University of Chicago and then made into something much smaller, also by Dan Bernstein of the University of Chicago, called Tweet NACL, which is the NACL cryptography library, but in the size constraint of 100 tweets. And the reason for this is because it's the world's first auditable high security cryptographic library. This library was made in order for it first and foremost to be easy to audit because of the small size and simple functions. And so it offers interfaces for Curve 25519, which is the public key crypto stuff, XSalsa 20, which is the encryption cipher, and Poly 1305, which is a HMAC cipher, but actually it's AES-based HMAC. It's really interesting. So the awesome thing about Curve 25519 is that it allows us to do elliptic curve Diffie-Hellman, and the public keys, as you saw, they're only 32 bytes. They're tiny. And it's also extremely fast. They can generate key pairs in milliseconds instead of minutes, like PGP. Let's look at the key derivation. This is the key derivation. We're going to go through it step by step. So this is what happens when you enter your passphrase, right? I said your passphrase derives your miniLock ID. So let's look what happens when I open miniLock, I enter my passphrase. How does that passphrase turn into a miniLock ID? Is it secure? What am I doing? Okay, so let's start here. User enters the passphrase. When the user enters the passphrase, so optimally, here's what we want to do. Optimally, we want the user to enter a passphrase that has 32 bytes of security, right? Because the private key of a Curve 25519, the private key into Curve 25519 is 32 bytes. It's 256 bits, right? And so we're going to derive our private key from the passphrase, right? And so ultimately, we want the passphrase to have 256 bits of security. Clearly, that's not going to happen. It's not practically feasible to have 256 bits of security in a passphrase, which is why
we go to the second step, which is entropy evaluation, to make sure it has at least 100 bits. How does this work? So basically, miniLock measures the passphrase and then suggests a long, unique passphrase that makes sense only to you. But this slide is actually out of date. This was how it used to do it. Now we have the construction of a suggested passphrase, which is basically this. miniLock ships with a dictionary of 58,000 most used English words. And when you want to generate your passphrase for the first time, miniLock gives you a 7-word passphrase that is basically the cryptographically pseudo-randomly chosen 7 words out of 58,000 words, which is 58,000 to the power 7, which means that you get to the power 111, which means that actually miniLock is capable of giving you, right off the bat, a cryptographically secure 111 bit of entropy passphrase without you doing anything. This is the new model of how we give users passphrases now. And there was new recent research done on how you can make people remember such a passphrase, but really it's actually not that hard, because this research done by Microsoft Research in Princeton shows that people are able to remember 56-bit passwords, right? And they focused on passwords, but the thing with passphrases is that they're sentences, and they make sense, and they're words that are related to each other. So it's easier to remember those passphrases. And because they're generated randomly, we can be sure that we're giving users passphrases that have certifiably 111 bits of entropy, which is enough for our purposes. But we can also, so it is enough for our purposes, but we can also work on making it harder to map the key space, right? Because what if you have the key space of all 111-bit passphrases, and then you just use that to generate a rainbow table, and then you're cracking all the passphrases. So that's why we use the scrypt key derivation function. Scrypt is a memory hard key derivation function. And that means that if you have like Bitcoin mining machines that have GPUs that are able to crack hashes very quickly because they're using GPU-based hash cracking, it actually wouldn't work on scrypt, because scrypt relies on RAM to slow down the key derivation, not on hashing, which is susceptible to CUDA style cracking. And so it's better than other key derivation functions. And it's actually 2 to the 17 rounds of scrypt. And now you might be wondering what the salt is, right? Because if we're using passphrases, where does the salt come from? It can't come from the passphrase. So this is why miniLock actually asks you, when you're logging in, to enter your email and your passphrase. And your email is just a unique identifier that acts as a salt. It's not used as an email. You could enter random garbage as your email. As long as you enter the same thing every time, it's fine. It's just a salt for scrypt. And then from that, you derive the curve 25519 key pair, which is the scrypt of the data. Get 32 bytes, L equals 32, and then you get the 32 bytes, you use them for the curve 25519 private key. And the miniLock ID is simply the base 58 encoding of the public key. And so base 58 encoding because base 64 has some weird characters like plus, and it also has I and L and 1, which all look the same, right? And so base 58 only uses characters that do not look the same, so that when you're communicating your miniLock ID on a business card or on your Twitter, or you're reading it to someone, or they're looking at it, reading it, they don't mismatch the characters. Base 58 is only limited to characters that look different. So it's a usability feature. And so the file encryption format, let's just go to the more interesting slide. All right. So here's how that works. This is a miniLock encrypted file. You have the, the header starts, and then you have the protocol version. You also have the ephemeral key, and then you have headers for each recipient, and then the header ends, and then you have the ciphertext. So let's look at the header part. The interesting thing about ephemeral keys is that the ephemeral key is used to encrypt something to the recipients, but it's generated only once and used only once, and it's only after they get past the ephemeral key encryption that they can decrypt their headers and get the actual key, the long-term key of the sender, which then can be used to decrypt the symmetric file encryption keys. And so once you decrypt the header for each person, so if you're person A, you decrypt header A, if you're person B, you decrypt header B, you get the file key, nonce, and name. The file name was actually moved. This slide is slightly out of date. And then you can proceed to decrypt the file. However, as we said, both senders and recipients are anonymized. So actually, we don't know which one of these headers is for person A and which one of these is for person B, or if any of them are for person A or B. So the senders are anonymized because the recipient must first obtain an authenticated decryption of the ephemeral key in order to obtain the sender ID, which is only possible if they are the intended recipient. And the recipients are anonymized because the headers, when they are shipped, are actually not shipped with any indication as to what public key they were encrypted to, what other public key was used to generate the shared secret. And so when you ship that, you have to actually, the recipient has to go through every single one and see whether they could obtain an authenticated decryption on one of them. And then they know that this is the one for them and they're the intended recipient. So let's see whether I can do, I think I have 5 minutes left, so I'm going to do a quick demo. All right. How to do, can you see the screen? Nope, okay. Great. All right. Okay. So here it is. I'm going to quickly enter my email. You don't see it. Okay. Thanks. Okay. 1 second. Actually, you know what? Maybe I'll just... Does anyone have a question? I can answer it now to save time while I set things up. Sure.
When you said that the App Store is code signing, does it also prevent the App Store from pushing new updates without notifying you?
No. The App Store can push updates surreptitiously without notifying you. That's true. You can disable new updates, and that's fine. However, the App Store is capable of pushing new updates because it itself is handling your signing for you. If you're worried about that, you can just download the app outside of the App Store and update manually. And so that's also offered as an option and should be offered for all applications. Yeah.
So you said the ID was only a function of your passphrase, right?
Yes, the email is used as a salt, yeah. But
Okay, but like if two people accidentally use the same passphrase, which happens with
yeah, sure.
are they going to accidentally impersonate each other? Or?
The question was, if two people use the same passphrase, will they be able to impersonate each other, or will they get the same ID? The thing is, they don't, because the salt, the email that you enter, acts as a salt, which means that your entire key space ends up being different, even if you enter the same ID. And this is because of the script key derivation function taking your email as the salt, and then using that in the key derivation function to produce an entirely different key space depending on the salt. And then even if you enter the same passphrase, the key space ends up being mapped completely differently. So as a result, that's what happens. Any other questions? Okay, well, it seems I won't be able to do a demo because of some weird display problems. However, I will quickly finish my presentation. So in terms of release, there's a Chrome app available, and there's also the spec and documentation and implementations in JavaScript, C#, Java, and Python. But also, this is not meant to be just its own standalone thing. This is meant to be a standard that you can implement into your own app, or you can wait for an upcoming secret project that I'm working on, which will implement it in a larger scale. And you can also get the code and documentation today at this website. So if you have any questions, please let me know. Yes?
Any process where you make
revocation. There's an open GitHub ticket on that. But yeah, revocation is not implemented yet. I didn't particularly think it would make sense because there is no centralized key exchange. However, I do understand that it's more useful than not. So there is a GitHub issue open, and I think it'll be in the next version for sure. Yeah. Yes.
Is there any lockout protection or brute force?
The thing is, so Scrypt takes a long time. The key derivation function inevitably takes a long time to derive the key. So for a single key, you have to wait like 5 seconds just for the calculation to complete. So it's not like we have to impose a fake delay, because even without a fake delay, the real delay is there. It's so slow, and it's intentionally made to be slow. It's intentionally made to be slow and use up a lot of your RAM on purpose in order to make it so that even if you have a really powerful system, it would take you a long time to go through all the key space. Yes?
So essentially, computer current design tied to the, well, not end of life, but whenever a script, if anything happens to that.
Yes. Actually, it's modular. You can replace Scrypt with another key derivation function, and you would still be, the rest of the encryption would still work. Your miniLock ID would change based on that passphrase. You would get a new miniLock ID. However, the old miniLock ID would still be able to, like, if you receive stuff off it, it doesn't mean that the symmetric encryption would change. It would like the resulting secret keys would still be accessible. But yes, it's a modular component. It's not going to break the entire thing if something happens to Scrypt. But it's unlikely that something will happen to Scrypt, really. Like so far as the research seems, it's not as studied as bcrypt or any of the other, or I would say at this point it's probably safe to say that it's better studied than PBKDF2, but that's about it. That's as far as I'm willing to go. Any other questions? Yes. Yeah, there was the question was, did I have peer review of the code? Yes, correct. There was a slide on this just a little bit while ago. It's a while back, but yes, there has been full peer review of the design specification, and you can see the results online. It's all there, and the code has actually been reviewed. The library that I wrote has been reviewed. There are independent libraries that other people wrote in Python, C#, and Java that I have not reviewed, and that I don't think anyone has reviewed, so I don't know about those. But the official library, yes, it has been reviewed. And the review results are also publicly published. So, well, I hope you take a look. You can check it out online. You can use it yourself to encrypt your stuff today. It has things, cool features like you can just drag and drop a folder, encrypts the whole folder, and things like that. But aside from that, it's also a good way to have a new standard that's, implemented, usable, open, and also easy for you to implement into your own applications as well. Thumbs up.